Okay. Hello, everyone. So welcome to the Quantum PC seminar. So today we are very happy to have Professor Nadish de Silva as our speaker to talk about efficiently achieving fault-tolerant quantum computation via gate teleportation. So Nadish is a Canada research chair in the Department of Mathematics. Nadish is a Canada research chair in the Mathematics of Quantum Computation and an assistant professor in the Department of Mathematics at the Simon Fraser University. So broadly, his research interests include quantum information and computation, non-locality and contextuality, and operator algebras and non-commutative geometry. So he is keenly interested in helping to elucidate the structural origins of computational and communicational advantages in both concrete quantum models and abstract classical models. So these questions sit at the foundations of logic, computer science, and physics, and involve disparate areas of maths, such as algorithms and complexity theory, functional analysis, number theory, and category theory. So today, to talk about some works about quantum, so Nadish, you have the stage.
Oh, thanks for the intro and the invitation, and thanks everyone for coming to hear my talk. Yeah, I think we can try to get questions throughout if something is really confusing, because it is cumulative. So if something is not clear, so I guess chat or something, and maybe somebody can, if I don't see it, somebody hopefully. Okay, so yeah, today I'm going to talk about some work that I did before joining SFU by myself, and then since joining SFU, this project has kind of grown to include collaborations with other people, both SFU and abroad. So yeah, broadly, I'll be talking about gate teleportation, which is a protocol that we use to do certain difficult gates in the setting of fault-tolerant quantum computation, and how to make that more efficient, and how to basically use some very high-level abstract maths to answer these questions. Okay, so the title is a bit of a mouthful, so I'll just talk a bit about the setting of this work, kind of put into context. So the setting is fault-tolerant quantum computation. So as we all know, quantum computation, you're manipulating matter and energy at atomic molecular scales, very, very sensitive to noise, and we have to try to keep it completely protected from the environment in order to maintain the integrity of our computation, or it'll quickly just descend into noise and not be lose the information that we're trying to work with. And so fault-tolerant quantum computation, this whole mathematical theory, involves applied mathematics, pure mathematics, CS, physics, electrical engineering, right? So it's a very interdisciplinary area where we try to deal with this problem by trying to protect our quantum data. And not only that, but once it's been protected, we also want to manipulate that quantum data in such a way where we don't assume that when we do operations on our protected quantum data, that those are perfect, because nothing's perfect physically, right? So there's a whole bunch of levels of protection going on in order to make quantum computing go from theory to reality, right? So I'll just point out that, in the 90s, when Shor came out with his famous algorithm that launched the whole field into becoming a very serious field, a lot of the reaction from experimental physicists at the time was, this is very interesting, but too bad we'll never be able to build it because noise is too much of a problem. And that's when this theory was constructed in response to that. Okay. So specifically within the setting of fault-tolerant quantum computation, I'm going to be talking a lot about magic states. Okay, so if you aren't unfamiliar, magic states are actual physical quantum states that are used as resources in fault-tolerant quantum computation. So in the scheme that we'll be talking about for fault tolerance, certain operations, certain quantum gates are very easy to do, and some are very difficult. And for the difficult ones, we're going to have a protocol that takes these magic states as resources and then uses them to execute some difficult quantum gate. And at the end, the magic state is thrown away. It's used up once every time you want to do a gate. And as it turns out, that this is kind of the most difficult part experimentally in terms of building a quantum computer, because you need so many of these magic states. And anything that we can do to make that process more efficient is going to bring us closer to having, usable and quantum computers. And also going to be talking a lot about the higher dimensional qudit settings. So rather than qubits, where if it's based on binary computation, zeros and ones, okay. I'm going to be talking about using higher level systems as our basic information unit. So it could be 0, 1, 2 labels for our kets, or up to literally any prime dimension. Okay, there are good reasons why this is now interesting, because it seems that fault-tolerant quantum computation might be more efficient in the qudit setting, and as I said, efficiency is the main obstacle here. So perhaps by moving to these higher dimensional qudit settings, we might actually reach fault tolerance faster. And also, I'm a mathematician, so I'm interested in taking results in dimension and trying to see how we can make them work in every dimension. And basically, that requires making our arguments much clearer and much more abstract and high level. So an essential point to understand this talk is that I'm coming from the perspective of mathematical physics, where we're very concerned with the mathematical methods that we use in physics and try to invent new maths that will make solving physical problems easier. Okay, so to give an overview of the talk, I'll first give a very basic introduction to quantum error correction and fault tolerance, just to remind you of the setting they're working in. I'll review quantum teleportation, and specifically gate teleportation, which is the procedure that we use to implement difficult gates. I'll give a little bit of mathematical background to understand the precise I'll be presenting. And then I'll talk about the results, which basically boils down to coming up with more efficient protocols for these difficult operations in quantum computing that are absolutely necessary for being able to do universal and fault-tolerant quantum computing. They also help us classify the resources that drive quantum computing. So as Kira mentioned, a large part of my research is also trying to understand the question, what is it about quantum physics that allows you to get an advantage in computing? So understanding this nature of quantum advantage at a very high level, abstract level. And so magic states are kind of a natural thing to study, because they take a very simple, easily simulable fragment of quantum computing, promote it to universality. So that's the reason why they're called magic states, because they seem to somehow grant a sub-universal quantum computer the ability to do quantum computing. And I'll talk a lot about the new mathematical methods that we need in order to solve this question that I'll be talking about. And in particular, it's going to bring in areas of math that actually have not really been applied within quantum computing before. So there's a lot of emphasis on development of mathematical methods. So specifically, the tools of math that we'll be using are linear algebra. Okay, that's not a surprise, considering quantum mechanics is all framed within the language of linear algebra. Abstract algebra, so like group strings and fields. So again, this comes up a lot in quantum physics. But what's new is that we're going to be using algebraic geometry, which is a very abstract, very pure area of mathematics that doesn't really find application very often in physics or applied sciences. Okay, so I'll start off with a little brief introduction to error correction and fault tolerance. So classical computers also have the same problem where data can be corrupted. So bits can be flipped, for example, if you have a cosmic ray hitting your RAM, that can flip a 0 to 1. And so in the classical case, we protect errors using redundancy, right? So instead of having just 0, if we want to protect that 0, we might encode it as 0, 0, 0 to just make copies of it, right? So that in case one of them gets flipped, we can just take a majority vote and figure out with high probability what was the bit that we actually meant. Okay, so 0 we would call our logical bit, and then 0, 0, 0 would be its encoded. However, we have this thing in quantum physics called the no-cloning theorem, which forbids this approach for quantum data, because we just can't copy data, because unlike in the classical case, we're not just trying to protect 0 and 1, but any superposition of it. So if we have an arbitrary superposition of it, we cannot just make copies of it, because there's a theorem that forbids it. However, and this part, very clever, it's still possible to encode quantum data in larger physical systems and introduce a sort of redundancy whereby we can protect quantum data. So here's a simple example of how we might use redundancy to encode an arbitrary qubit. So if we start off with some qubit, alpha 0 plus beta 1, we can just use the C-naughts to copy, to sort of just expand 0 into 0, 0, 0, 0, and 1 into 1, 1, 1. Okay, so notice that this is not making 3 copies of our original state, alpha 0 plus beta 1. Okay, this is because if we did actually just take 3 tensor products of that, which is the same thing as making 3 copies of it, we would get all these cross terms. Okay, so what we're doing is we're copying in the fixed standard basis. But we can still work with this in terms of encoding data for error correction. Okay, but the problem is that we can't actually, once we've encoded it, so once we've encoded our data as say 0, 0, 0, and 1, 1, 1, we can't actually do the same thing that we did before, which is take a majority vote and see. We can't actually look at the quantum data once it's been encoded, because that's essentially measuring it, and that would you would have wave function collapse and you would destroy the data that you were trying to work on. So the problem is maybe you can encode your data, but how do you tell if there's an error or not, and how do you correct them if you can't even look at the data? And the very clever way around this is you don't ask the question of what is the data once it's been encoded. Instead, because that would destroy the data, instead you ask the question, how has the data been corrupted? Which doesn't tell you what the data is, it just tells you whether there's an error or not, and what kind of error it is. So you can get that information through measurement without actually affecting the data, which is quite a clever scheme. Okay, so once we've done that, we can figure out how the data is being corrupted and apply appropriate corrections. And once we have our data encoded using one of these schemes, we want to be able to compute on it, right? So once it's been made redundant in this way, we also want to do quantum gates directly on the encoded data. So we don't want to move between the pure form and the encoded form every time we want to do a gate, because that's just giving lots of opportunities to introduce errors. So we want to figure out a way to do our operations on the logical operations we want to do on the actual physically encoded data. So the optimal way we can perform a gate on encoded data in a way that's fault tolerant, which means that we want to do operations where we might make mistakes with some probability, but still be able to control the rate of errors that this does, is to do gates transversely. Okay, so when that means is that so on the right, we have some gate that we want to do on our logical data, right? And then on the right-hand side, each logical qubit has been encoded into 3 qubits. And what this diagram is telling us is that if we want to do C naught on the 2 logical qubits, all we have to do is do C naught pairwise on in parallel on these encoded qubits. Okay, that's the best way to do it, because this way errors don't spread, because every line in the first block of 3 only touches 1 line in the second block of 3. If they touch locked lines, then it could propagate all over and errors could spread out of control. So optimally, we want to do gates this way. However, not all gates can be performed transversely, unfortunately. That's a theorem, the Easton-Nil theorem. So we can try to maximize the class of gates that we can do transversely, and then make the class that we can't do as small as possible. And we also have to figure out some way to do those ones that we can't do transversely. Okay, so the way that we do that depends on the particular choice of error correcting code that we use. So right now, I'll give us a little recap on stabilizer codes, which are kind of the most standard way. It's a family of error correcting codes, which is ways of encoding your logical data as physical qubits. And in particular, I'm going to be talking, you maybe have already learned about stabilizer codes, probably in the binary case with qubits, but it's basically exactly the same in this higher dimensional qudit setting, where instead of 0 and 1, we might have 0, 1, 2, or 0, 1, 2, 3, 4 levels, most higher level systems. Okay, but the same, the math is very similar. Okay, so you probably know the basic Pauli gates, Z and X. But for the qudit setting, Z and X are operators are unitaries on D level systems. Okay, so we're going to let D be any odd prime, so like 3, 5, 7, and so on. And we can define Z to be, so in Z normally would be 1, -1, but instead we're now going to have these primitive teeth roots of unity. So for example, all along the diagonal, that's the Z operator. Okay, so it would be like 1, and then a 1/3 rotation around the circle, unit circle, and then a 2/3 rotation around the unit circle. Okay, if D is higher, then you have more entries and more refined angle on the circle. And X is the shift operator. So you just take the identity operator and move all of the columns, shift it one to the left. Sorry, yeah, to the left. Okay, so in the case where t equals 2, this is the standard that an X you're familiar with. Okay, and what's important about these Z and X is that they satisfy the Weil canonical commutation relations. Okay, so this is actually kind of more important than the actual entries of the matrix themselves, as we'll see. What's more important is that the algebraic relations they have between them. So both Z and X are order D, so if you raise them to D power, you get the identity. And if you want to move a Z past an X, you're going to introduce the root of unity, this phase of 1 over D rotation around the circle. Okay, so again, generalizes what we have in the binary case, where Z and X square the identity and omega would be -1. Okay. So we can define, once we define the basic Pauli gates, we can define the more general ones, basically by taking powers of Z and X to some integer, and then you might have, so if Z and X both have order D, that means you can raise them to the power of 0 to D minus 1 before you go back again. And if you have n qudits, then that means you have Z and X on each qudit, and each one can be raised to a different power. So here P and Q are 2n integers mod D. So that just means, you go 0 to D minus 1 and then 0 again. So it just kind of repeats, like you just take the modulo D. So we have 2n integers mod D. So we split them up into a P vector and a Q vector. Then we can define this more general Pauli where we just raise Z1 to P1, multiply it by X1 to Q1, and then as a product with the same term going on with P2 and Q2 and so on. Okay, and the canonical commutation relations, which told you that if you want to move Z past an X on the same qudit, introduces a factor of omega, that means we can immediately find a condition for when these more general Paulis commute, which is basically counting the number of times you have to move Z and X past each other, and you get this product, which kind of looks like an inner product, but the P is dot product with the second half of the second one, so P dot Q, and then minus P prime dot Q, because the negative is because you're moving Z the other way across X's, so they introduce omega to the -1. Okay, but basically, just from the information of the powers that you raise Z and X to, you can come up with a simple condition of when Paulis commute. That's going to be important. Okay, and so we can define a group of Pauli gates, which are basically just all the possible ways of multiplying Z and X on each qubit, and also with any phase that can be a primitive root of unity. Okay, you multiply these together, you're going to get something back in this, that's a Pauli gate, so that's why it's a group, essentially. And we're going to label it C1 for reasons that will become obvious later. Okay, so these Pauli gates play an essential role in defining stabilizer codes. So basically, we're going to use eigenvectors of these Pauli gates, or at least of large groups of Pauli gates. We're going to use their common eigenvectors to encode quantum data. So these eigenvectors of Pauli gates are called stabilized states. So they're going to be used to encode 0, 1, or 0, 0, 1, 1, instead of the choice of what stabilizer code we're going to be using is basically a choice of which eigenvectors we use to encode them. So if we're using one of these stabilizer codes, the question is which gates can be easily performed fault-tolerantly, that is transversely. So these gates are a very important class because they're the ones that we can immediately do easily. And in most of the cases of interest, relevant, the codes that people actually use, the group of Clifford gates can be performed fault-tolerantly in an easy way. Typically, we mean transversely. That could also mean, sometimes more general things, but they're also still easy. But basically, the slogan is Clifford gates are easy to perform in stabilizer codes. So Clifford gates, they are gates that conjugate. Whenever you conjugate a Pauli, you get back a Pauli back. Okay, it's a different Pauli. It just takes some products of Zi and Xi and gives you back some other products, maybe with a phase that's root of unity. Okay. So, and you're probably familiar in the qubit case, it's generated by ZX, C0, and Hadamard. Okay, so this this definition that it conjugates this group and to give you back something in the group has a terminology in group theory. So the Clifford Gates is also known as the normalizer of the Pauli group with the unitary group. That just means it conjugates the group back. The subgroup of the unitary group gives you something back in the group. Okay, and because it conjugates Paulis to Paulis, so remember that Paulis, even though they are ostensibly on the surface these big complex matrices, exponentially sized unitaries with complex entries, we've seen that they conjugate Paulis to Paulis. And Paulis themselves, we saw, are actually described by a few integers, right? 2n integers, and the integers are bounded, right? The integers can be between 0 and d-1. Okay, so what this line is saying, so the /t is just telling you to forget about the phase. So we consider two Cliffords to be the same if you can multiply it by phase and get the other. So if you forget about the phase information, then all the information of a Clifford is actually just going to be encapsulated by this matrix, a small matrix of size 2n by 2n of integers that basically tell you what Pauli gets mapped to what Pauli. And so this is the essential point that, and kind of the basic idea behind the Gauss-Menil theorem is that Cliffords, even though they, as a complex matrix, they're quite big and involve these very complex numbers that can be, have very arbitrary precision. Actually, there's a much more compact representation, which is polynomially sized, with just these 2n by 2n matrices of integers that are called symplectic matrices. Okay, so the essential point is that Paulis are described by a small amount of discrete data rather than continuous complex numbers. They're represented by a few integers. And Cliffords, therefore, because they map Paulis to Paulis, are also defined by a few integers. Okay, so the problem with the Cliffords, even though we can perform them fault-tolerantly quite easily, is that it's not dense in the subgroup of unitaries, which means that we cannot do universal quantum computation with just the Cliffords. We can't reach every gate with arbitrary precision. We need to be able to perform at least one non-Clifford gate in order to get universal quantum computation. And as we saw, the Easton-Dill theorem rules out being able to do every gate transversely, no matter what your error correcting code is. So that means we're always going to be faced with this problem. So we need to find some way to do a non-Clifford gate, and that will supplement the easy Clifford gates and get us universal quantum computing. Okay, so the way that we typically do this is a variation of quantum teleportation, where instead of moving a qubit from one place to another, we move the qubit, and when it appears on the other side, it has some gate applied to it. Okay, so I'm just going to quickly review teleportation and explain how gate teleportation works. But probably everyone's familiar with quantum teleportation. So Alice has the state psi, and she wants Bob to have psi, but she doesn't want to physically send psi to Bob. Okay, but they know that they're going to do this task. So in advance, they prepare a Bell state, maximally entangled state, and they take one half of it each. Okay, so Alice has the state she wants to send, and she has one half of a Bell pair. Bob has the other half. Alice does a Bell measurement on her half. And as a result of wave function collapse, Alice's pair is now collapsed to one of the Bell states, and she gets an outcome that tells her which one it is. So she gets some two numbers, Z and X. And Bob now has psi, but there's some Pauli applied to it, right? And in order to know what Pauli is applied to it, he needs the numbers Z and X. And without those numbers, from his perspective, he has a maximally mixed state. So basically, nothing's happened until Alice sends the information about how to correct his state, and then he applies the proper correction using that classical data, and now he has psi. Okay, so this was like a variable communication protocol just to blow people's minds, but it turns out to be actually very practically relevant. Okay, so here is teleportation. Sorry, here's the teleportation protocol in circuit form. Beginning. Alice is the first two lines, Bob is the last line, and they start by sharing a Bell pair between the two of them, and Alice has some state psi. Okay, so the first box is the preparation of the shared Bell state. The second box, dashed lines, is the Bell measurement by Alice, and the last box, the third box, the X and Z, that's the correction that Bob has to do in order to recover psi at the end. Okay, so we're going to basically modify this protocol very slightly by introducing this gate G that we want to do. Okay, so what I've done here is, just so you see, there's a G now applied to Bob's half of the bell pair, okay? And there's also a G star right after that. So inserting that G and G star is basically doing the identity. So actually, it doesn't change anything. But what we've done is we've inserted the identity and moved the G and G star into two different boxes because they commute with what else is doing. And at the end, we add a G, and that shows up in the state that Bob gets. So we apply a G. So instead of having psi at the end, we get G psi at the end. So just to see quickly, we just added those three components. Okay, so the purpose of doing this is that now Alice sends Bob, and where she had psi, Bob now receives psi, where G is some gate. Okay, but it means that Bob has to do G on the bell pair. Okay, but what's interesting about this is that you can prepare that bell state to it well in advance. If you know you're going to do 100 times G, you can prepare that state in advance and use them as needed. And also, because you might make a mistake when you apply G and introduce some error, it's better to introduce the error on some bell state that you can throw away rather than on psi, which is very delicate, sensitive data that you want to try to protect. That's in the middle of a computation. Okay. And so this also motivates the definition of a third level gate. So I defined C1 to be the Pauli gate, C2 to be the Clifford gates, and C3 looks very similar to the definition of C2, the Clifford gates, where G is third level if when you conjugate a Pauli, you get back a Clifford. Okay, so originally a Clifford gate conjugates Paulis to Paulis. Now third level gates conjugate Cliffords to, Paulis to Cliffords. Okay, and the reason why this is interesting is because when G is third level, that means this third box, G star X Z G, that's going to be Clifford, right? It's a conjugation of a Pauli by G. And if it's Clifford, that means we can do it fault-tolerantly. So Clifford, the third level gates are important because that means that this whole gate teleportation circuit can be done fault-tolerantly. Which means that in order to do G, we can now do G fault-tolerantly as long as we have access to this bell state that has had G applied to it. Okay, so basically we do G advance on kind of a scrap piece of paper, and then when we need it, we can apply it fault-tolerantly. So this moves all of the difficulty of doing G from doing it inside a circuit to preparing some nice state. And these states can be prepared fault-tolerantly. So it kind of shifts these gates G, which are hard to do, from having to actually perform them directly on the data that you want to instead preparing from what we call a magic state. And we can also define levels. So the third level are things that conjugate Paulis to Cliffords, and we can also define things that conjugate Paulis to third level gates and so on. But I won't talk too much about that. But there is a whole sequence of gates that we can do fault-tolerantly called the Clifford, and they form a sequence of sets: C1 Pauli, C2 Clifford, C3 third level, and C4 and so on. I'm mostly going to talk about C3. Okay, so notice that with this protocol, the magic state, which is that first box, it has twice as many as the gate G, because we have to have a bell pair and apply G to only one half of it. Okay, so that means the magic states, which we have to have a magic state every time we want to do G, which could be thousands or millions of times in a computation. There's a lot of possibly wasted space here because we're applying G to only one half of a bell pair, double the number of qubits that we want, or qudits, if we're trying to apply G. But we can act a more compact gate teleportation protocol that doesn't use a bell pair. Okay, instead we the state a gate that we want to the plus state. Okay, so that means that the magic state that we need to prepare in order to do this gate has the same size as the gate we want to do. But the problem is in order for this protocol to work, the gate that we want to apply has to be a diagonal gate, or it has to be a diagonal gate multiplied by Clifford on the left and right. Okay, so that motivates this definition of semi-Clifford gates. So it's an unfortunate terminology, but basically what it means is a gate is either diagonal or diagonal up to Clifford, which means it's diagonal if you multiply on the left and the right by possibly different Cliffords. Okay. Basically, what that means is that if a gate is of the special form, that means you can use the special compact protocol. So just to recap everything, because it's a lot of information, the Pauli group, C1, are gates that are built from the basic Pauli gates Z and X. The Clifford group are those C2 are the gates that can be easily performed fault-tolerantly. However, these aren't enough to have a universal quantum computer. The third level gates are the ones that can be performed fault-tolerantly as long as you have access to suitable magic states. And preparing and storing magic states is kind of one of the most difficult aspects of building a quantum computer, fault-tolerant quantum computer. And the semi-Clifford just means they're gates that can be performed with more efficient magic states. So they're so semi-Clifford third level gates are kind of the best gates that you want to do if you want to achieve universality. And you only have to be able to do one of them, because once you have one of those that's outside the Clifford group and all the Cliffords, then you can do every gate. Okay, so this motivates two natural questions, which have been studied for about 25 years since Gautam and Chuang came up with this whole scheme. So the first question, what are the gates of the Clifford hierarchy? So in the literature, basically you're just going to find examples, like the T gate is probably the most common example, is the third level gate, okay? But there's just kind of random examples here and there like that, rather than a systematic way of knowing what they all are. There are some results about that, but we don't really have a complete classification yet. And there's another really important question is which hierarchy gates are semi-Clifford, because those are the ones that are the best gates that you want to do. They're the ones that have these efficient protocols. So just to review a few of the known results. So in the qubit case, so D equals 2, if you only restrict yourself to 1 or 2 qubit gates, then all of the gates of the Clifford hierarchy are semi-Clifford. Okay, that's a result of Zheng, Chen, Chuang. However, if you go to more number of qubits, so 3 or more qubits and third level or higher, then not all gate level gates are semi-Clifford. So here is a chart of the number of qubits on the bottom, and vertically is the Clifford hierarchy level. So the black dots indicate that for this number of qubits in this level, everything is semi-Clifford. Being in the Clifford hierarchy also means you're semi-Clifford. And if it's a white dot, that means there are known examples of Clifford hierarchy gates at that level that are not semi-Clifford. So it depends on the number of qubits and on the level in the qubit case. Okay, so what I'm going to talk about is basically trying to extend that first result, 1 or 2 qubit gates, all of them being semi-Clifford, and try to make that work for qudit dimensions, so for any D. So I'm just going to quickly review some of the math that go into this. A little bit of mathematical background. The von Neumann theorem is a foundational result of quantum theory, originally meant to unify the matrix and wave mechanics pictures of quantum theory. Okay, so there were originally 2 different mathematical formalisms, and everybody was wondering why are there 2 different formalisms of quantum theory that give the same predictions. And Stone and von Neumann basically proved that they're actually representing the same theory, the maths are the same. And roughly it's saying that any 2 representations of the canonical computation relations are unitarily equivalent. So matrix and wave mechanics both manifest the canonical computation relations, so they're actually the same. And even though this result is very and had a very different original purpose, it turns out that it's actually perfectly suited to studying the Clifford hierarchy. And that was the thrust of some work of mine from 2020. So just to tell you what the discrete Stone von Neumann theorem is, we're only going to look at like this finite dimensional case. So suppose U and V satisfy the canonical computation relations. So U and V have the same algebraic properties as X and Z. So they both have order D. And if you move U past V, that introduces an omega, comparative root of unity. Okay, that means U and V look like Z and X. And it turns out that they are basically Z and X, which is to say that they're Z and X up to unitary rotation. So if U and V satisfy these 2 algebraic conditions, then that means there is a G that conjugates Z and X to U and V. And so what this tells us is that unitaries can be, there's a bijection between unitaries and pairs of unitaries that satisfy these algebraic relations. So you go from G to U and V by conjugating Z and X. And conversely, if you have U and V that satisfy these relations, you can reconstruct G that conjugates Z and X to U and V. So basically, we're going to be studying Clifford hierarchy gates, not by studying G itself, but by studying the images of Z and X under conjugation by G. And it's naturally suited to studying Clifford hierarchy because we can use the definition and observe that a gate is Kth level if and only if U and V, which is the conjugation of Z and X by G, generate K minus 1th level gates. So it kind of fits exactly with this inductive definition of the Clifford hierarchy. So if you take that perspective seriously, then you get a framework for studying the Clifford hierarchy using the Silva-Neumann theorem, and it gets you a bunch of nice results immediately. For example, it lets you generate the Clifford hierarchy either algorithmically, so you can just write a program that will generate every Clifford hierarchy gate, which we didn't have before. We just kind of had some examples here and there, but now we can get the complete Clifford hierarchy. It also gives you a nice way of looking at a gate and asking whether it's semi-Clifford or like a nice criterion for telling you when a gate is semi-Clifford. You can also prove that all 3rd level gates of 1 qudit are semi-Clifford. Okay, so that's kind of 1/2 of the result of Zhen Chen Zhuang that I mentioned earlier in the qubit case. This was known. I should also mention that Zhen Chen Zhuang, their proof of every gate being semi-Clifford, they actually relied on exhaustive computation. So basically, they asked the computer to look at lots of cases. So it doesn't actually really apply the case of higher dimensions or infinitely many dimensions, because you can't run a computer on infinitely many dimensions. So it really requires proving things, mathematically rather than relying on a computer. And so that only talks about 1 qudit gate, but we also need 2 qudit gates. And so using this perspective, I managed to prove that for 2 qubits, every 3rd level gate is semi-Clifford. But again, that's only for 1 single dimension. So it's not really satisfying because we want to know what happens for an arbitrary dimension. And so the tool that we're going to use to prove this is going to involve algebraic geometry, which is a very abstract area of maths. So I'll just really briefly give the idea. The idea is to study algebra via geometry and vice versa. Okay, so just like the title, same. You're probably familiar with algebraic geometry a little bit implicitly because you learned some in high school, and it traces its origins back to ancient questions that the Greeks were thinking about. So the parabola, it's the solution to a quadratic equation, right? So there's a link here already between geometry and algebra. The geometry is the shape of the parabola, and the algebra is the quadratic equation that defines it. Okay, so if you moved all the letters over to one side, it would just be some polynomial in 2 variables, a degree 2 polynomial. You want to know when is that polynomial equal to 0, and the answer is when you lie on the parabola. Okay, and on the right-hand side, you have a more complicated object, a solution space to some polynomial, which we call an algebraic variety. So the generalization of a parabola to any number of variables or any dimension called an algebraic variety. So here, this is a 3-variable, the solution set to a 3-variable polynomial, and I think it's a quintic, so degree 5 polynomial. Okay, and not only, so algebraic geometry studies these connection between the polynomials and the shapes they define, but also goes into very abstract territory. So the variables in the polynomial don't necessarily have to be real, no complex numbers. They can be integers in some other weird number system. Okay, but the general idea is that we have to understand the space of solutions via the polynomial equations that define them, and vice versa. And so there's a connection here. There's a bijection between algebraic sets, which are these solution spaces, and radical ideals, which are just basically algebraic objects that are defined by certain polynomials. So basically, you can move back and forth between these descriptions as necessary in order to solve whatever question you're thinking about. So basically, the idea of the proof is, instead of using the unitary way of looking at gates in terms of thinking of them as unitary matrices, we're going to be thinking about them as the integers that define them. And we're going to come up with a bunch of polynomial equations that tell you when a gate is 3rd level. And that's going to define some space, some shape. And we're going to find another bunch of equations that tell you when that 3rd level gate is semi-Clifford, which is going to also give you a shape. And we're basically going to show that the 2 shapes are the same, which is going to tell you that every 3rd level gate is semi-Clifford. Okay, so that's basically the thrust of this work, which is a collaboration with Imin Chen, who is also at SFU in the math department, and he is a pure number theorist. So he doesn't really do quantum computing at all. He mostly works on, like Fermat/theorem related questions, but that's the kind of expertise that was necessary in order to make this argument work. So the theorem, we already talked about the one qudit case. So now we're going to prove that every two qudit third level gate is semi-Clifford. And this is going to work for any odd prime dimension. So making it work for infinite dimensions is basically the reason why it starts involving this very complicated area of math. Okay, so as I mentioned, the proof strategy is to characterize third level gates using unitaries, but using polynomial equations over ZD, because as I mentioned, Pauli's and Clifford's, they're basically defined as a string of integers, a small string of integers. And then we're also going to define semi-Clifford third level gates also using these integers and showing that a gate is third level or semi-Clifford respectively, if and only if the integers associated with it satisfy some polynomial equations. And then we're basically going to show that for every dimension, the two spaces that these equations sets define coincide. And that's basically going to prove the theorem for one fixed dimension. And then if we want to make the theorem work for infinite dimensions, that requires this theory of schemes, which is basically a very, very modern and abstract presentation of algebraic geometry that's kind of used a lot in number theory and things like that. Okay, so basically I'm just gonna explain how the idea of how we do this. So let G be some third level gate, right? And so it's a two qudit third level gate, and we want to show that it's semi-Clifford. So the definition of third level is that if you conjugate some Pauli, you get back a Clifford. Okay, so because it's two qudits, that means there's four basic Paulis, Z and X on the first qudit and Z and X on the second qudit. Okay, and being third level means that if you conjugate each of these by G, you're going to get back Cliffords, right? So it's C3, which means if you conjugate a Pauli, you get something in C2, which is Clifford. And so remember that Paulis are defined by 2n integers mod D, and Cliffords, because they map Paulis to Paulis, they can be characterized by, instead of using a big unitary, you just use this very small matrix of integers that tells you which Paulis get mapped to which Paulis. Okay, so that means these four objects, G, Z, 1, G star, G, X1, G star, and so on, these four Cliffords, they're all defined by a very small number of variables. Okay, so the first step is to basically establish that all of these four gates that are going to define our third level gate have a very simple form that basically boil down to a 2x2 symmetric matrix of integers and P and Q, which labels some Pauli. So basically, each of these four Cliffords requires 7 variables to describe, where each of those variables is a number between 0 and d-1, like a integer between 0 and d-1. And so that massively simplifies the question already. And so the question is, given a bunch of integers, so 4 times 7, so if you have 28 integers, when are those integers coming from a third level gate in this way? Okay, so basically what we do is come up with a bunch of polynomial equations that perfectly characterizes the third level gates. So it's a bit complicated, so don't try to read it right now, but basically these are equations involving the variables that define the Cliffords that you get by conjugating a Pauli by a third level gate. And essentially what these equations are enforcing is the canonical computation relations, because basically those Cliffords that you get by conjugating Paulis also have to obey the canonical Clifford canonical computation relations, because algebraic relations are preserved by conjugation. Okay, so this is basically saying that the first two GZ, G star and GX G star, you can move them past each other and it only introduces an omega, just like Z and X. So if you bundle together all those conditions, you get this set of equations. And the next thing you want to do is characterize when those integers that describe some third level gate is also semi-Clifford. So it turns out you can also do that quite easily. So this, it looks like 3 determinants because it is. But yeah, basically that we just are able to tell when a gate is semi-Clifford just in terms of the numbers that describe them. And so what we want to do is, now that we have one set of polynomial equations that define third level and another set that tells you when it's semi-Clifford, we want to show that those 2 shapes are the same. And we move from geometry to algebra, and that basically involves showing that 2 algebraic objects called the radical ideals of those shapes are the same. So if you fix the dimension, then that's pretty easy to check. But if you want to make it work for all dimensions at once, then you have to go to this very abstract area of maths, where you have to, instead of constructing these algebraic sets, you construct these schemes, which are just like very, very abstract forms of algebraic sets, essentially, and then do the calculation on those geometric shapes, and then reduce modulo d, and that gets you what you want. So if you had fixed the dimension, you can check that these polynomial systems define the same shape algorithmically using a computer algebra system. But unfortunately, this system is too complicated because there's so many variables and the equations are way too complex. You can't just plug these equations into a computer. So instead, we have to make some simplifications by basically weakening some of the polynomial equations. So this matrix here, this matrix equation, is one of the set of equations that we use to define third level gates. And we've moved a bunch of stuff to the right-hand side. So it's not actually linear because the stuff on the right-hand side is actually quadratic. So instead of asking that the solutions to the equation, we just look for, we just forget about the right-hand side, which has all the quadratic terms, and ask whether the system is consistent, if there could exist a solution. So what this does is eliminate these PI variables. So that makes the system simpler for a computer to analyze, but it also enlarges the shapes that we're dealing with, which possibly introduces more points that don't correspond to any third level gates. So the last step of the proof is to show that these new components that get added once we weaken our system don't actually correspond to actual gates. And that actually is basically the idea of the proof. So I'll just summarize by saying that the point of all that very, perhaps seemingly needlessly complicated math is that it does have a very practical upshot, which is that we get much more efficient paths to achieving universal quantum computation. So many more gates that we can do in order to achieve universal quantum computing. And it applies for any dimension. And you might seem like you might think that you might never actually use qudits in real life, but it turns out in the theory of fault-tolerant quantum computing that qudits are actually much more efficient for preparing magic states, which is the huge bottleneck in fault-tolerant quantum computing. It's also quite relevant to understanding quantum advantage theoretically, because basically it tells us a lot of information about how powerful different magic states are. So that helps us understand what resources drive quantum computing. And as I mentioned, from a mathematical physics point of view, it's interesting because it's kind of the first time anyone's applied these kind of tools from algebraic geometry within quantum information. So hopefully it'll be the start of a lot of questions, I think, in error correction and fault tolerance could be approached by basically reformulating the interesting physical question, as the equivalence of 2 algebraic varieties. So hopefully people will be able to use these same tools in order to answer their own interesting questions about error correction. Okay, so thanks a lot. We'll open up to questions.
Questions? Yeah, there's one from Zoom. Josh, you can ask first.
Hi, great talk. I'm Josh
Thanks.
Mutis from Rigetti Computing. I live in BC, so I just kind of join these when I can. But really interesting. So I'm just trying to understand how this fits into, you're mentioning algorithms. So when I think of a quantum algorithm, I break it down into like Clifford and plus T. So to try to get to some arbitrary angle, right? And So I looked through my algorithm for like the arbitrary angles and I do some sort of like gate synthesis or something to express them in like H's and T's. And what you're talking about, having like a richer vocabulary of non-Clifford angles to reduce that overhead, or is it something else?
Yeah, no, that's essentially it. Instead of doing it over Clifford plus T, it just means you can replace T with any of these, it basically is telling you everything that you could replace T with, and the ones that are actually have the same properties of T. There's a reason why we chose T, which is basically that it's semi-Clifford and third level. So there's actually, a whole rich family of gates that have those same properties.
I see.
That are basically as good as T. And yeah, it may turn out that rather than, once it's just kind of, it's potentially thinking very far ahead in the future, right? Like for now, maybe we only have the technology to be able to do T very easily, and it might be too hard to implement lots of other, have stores of other magic states. But it could be that when we have good, experimental control, when our is improved, that it might actually be better to have a much richer family, because rather than doing 100 T gates to get you some other third level gate, you just do that third level gate directly.
I see. But it obeys these same properties that you could do. You would be able to find like a state distillation and a teleportation scheme that you could then implement it in your fault-tolerant quantum computer.
Yeah, essentially, yeah. It has its efficiency of gate teleportation is the same essentially as the T gate. So the T gate is kind of optimal. So these are a bunch of other gates that also have that same properties.
Cool. Okay. Thank you.
So there's a question from chat that Adrian said, are there any interesting open questions you would like to highlight that could be approached using a scheme theoretical technique?
Yeah, so I mean, this is very recent work. So like basically, I've just been thinking about this question and getting it wrapped up. But I do think that there are, I mean, I've gotten like, emails from someone at Waterloo who also was working on questions basically to do with exact synthesis, gate synthesis, where they felt that these tools could be used. So I mean, I can't really talk about it because it's not my work, and also I don't fully understand it yet. But I do think that there are, basically, I mean, it's very broad, right? Because it's basically the fact that it schemes, it makes it sound like it's more complicated than it is. I mean, the actual theory of schemes is quite complicated, which is the reason why, even though I'm a mathematician, I had to work with a number theorist in order to do this, because even in order to like prove something with schemes, you basically have to have a PhD in it, because it's just so complex and takes so long to absorb and understand all the definitions. But the idea of it is very simple, which is that if you have a question and you can reduce it down to showing that being a solution to one set of polynomial equations implies that it is a solution to another set of polynomial equations. If you can turn your question into a question like that, then you can use these techniques. And I mean, the key thing is if you need it to also work for any dimension, right, then you need to start using these scheme theory techniques. If you want to do it for a single fixed dimension, then you can just use the computed algebra system. But if you want to be able to prove a statement like that for any dimension, then yeah, you have to basically essentially use these scheme theory techniques. The thing is, like, it's not like a super complicated application of schemes compared to what people in number theory are doing. It's just that in order to justify theoretically the calculation, you just have to use this slightly sophisticated mathematical technology. But the idea is very simple. If you just want to show that being a solution to one set of polynomial equations is a solution to another, which is, I think, quite a broad set of questions, for basically the reason that I talked about earlier, which is that everything in error correction, they're all based on stabilizer codes. And what are stabilizer codes based on? They're based on these Weyl canonical commutation relations, right? So you don't have to actually really work most things in, like the whole lesson of the Gauss-Meinel theorem and stabilizer codes is to not work with the states, but to work with the algebra of how Clifford's how you have this more compact representation in terms of integers, which is describing Pauli's, and Clifford's are matrices, also describing integers, right? So everything in error correction kind of naturally lends itself to being phrased in terms of integers, and a lot of questions can naturally be phrased in terms of polynomials involving those integers, right? So this work is an example of that. So on the face of it, you wouldn't necessarily think that whether something is third level or not is defined by a polynomial system, right? Because being third level is defined in terms of unitaries and matrices, and it's in terms of matrix multiplication. But if you work at it on the level of the algebra, like, kind of take the Gauss-Mendel perspective of it, then this matrix equation actually turns into a polynomial equation. And the semi-Clifford condition also unexpected, at least to me, that you could phrase it in terms of polynomials, but it turns out it does have a very natural and simple description in terms of polynomials. So you wouldn't necessarily think that questions about whether something can be, have an efficient gate teleportation protocol, which is a very physical question, can be analyzed, and very explicitly about matrices and unitaries, has this very simple description in terms of integers and polynomials. So I think that a lot of questions in the same setting of error correction, they would have, they could be reformulated in terms of polynomials. And then if you were interested in solving them for all dimensions, then yeah, you would need these kind of techniques. So yeah, I hope that answers your question.
I have a question. Can you give an explicit example what a qubit magic state look like? And do you know of any distillation protocol that exists about this kind of magic state?
Yes. So let me go back to the slide. So actually, yeah, very early. Yeah, okay. So see this Z, this definition of Z, right? One omega squared and so on, right? So that is, you can define that with a polynomial, right? Because it's, it's diagonal, right? So there's only D numbers you have to define, right? The first one's labeled by 0. The 1 is labeled, the omega is labeled by 1, right? So this you can describe this with just a polynomial phi, right? So it's actually just omega raised to the number that along the diagonal. Do you see that? Like the first one, the top left corner is Z, is omega to the 0, right? And then the next diagonal entry is omega to the 1 and omega to the 2, right? So that's a linear polynomial. So if you take Z, if you take that polynomial to be like, say, Z squared, then that's going to get you a Clifford. And if you take Z cubed, that's going to get you a third level gate.
Right? I see.
So, yeah, so there's also, I mean, that's not the natural T third level qubit gate, but that does, it is basically that. So there's this paper by Howard and Vala called like the qubit T gate or something like that, where they explicitly define the T gate for qubits. Maybe they even do it for qudits. There's also this paper by Kui, Gaudsman, and Krishna, where they classify all the diagonal Clifford hierarchy gates. So there you can find all the third level diagonal gates in that paper. So what was the second part of the question?
No, I'm asking the first question because I think the experimenters were looking for something to implement, and it seems that at least I am not aware of any implementation of qubit magic gates or magic state. So experimenters, if you're looking for something to do, probably is something that you can try in your system. The second,
oh, sorry. The second question was, I think you asked about distillation.
No, I'm just telling the experimenters to do something.
Oh yeah. No, I have lots of ideas.
Yeah, and the second question is, so do you know? So you talk about magic state for qubit and qudits. Do you know if there's any magic state distillation protocol for this kind of a high-level magic state?
Yeah, yes, right. So the paper to look there by like Dan Brown, and Earl Campbell. I think it's called like magic state distillation in higher dimensions or something along those lines. But yeah, people have worked out the distillation protocols for higher dimensions. And the reason why it's interesting is because it turns out to be orders of magnitude more efficient for some reason.
Great, thanks. Any more questions from here? Any more questions from the Zoom side? I don't see any. It's a good timing here. So thanks, Nadish, for your talk today. Very nice. And yeah.
Cool. Yeah, thank you. Cool.
Thank you.
Happy to. Yep. Take care.
Have a good day.
Thank you, Nadish. Thank you so much. And Josh had just left a question for maybe offline, that maybe you want to be in touch with him to chat about. I don't know. Can you see that in the chat there?
Yeah, I just see that showing up.
I know we're out of time, but maybe that's something you can ask later.
Yep. Okay,
Thanks.
bye, everyone.
Cool. Yeah. Thank you. Bye.
Bye.